Okay. Hi everyone, welcome back to my YouTube channel, the Math Aficionado. Today's video is going to be our video on the chapter number 5, which is more about the 4 rules of the arithmetic. Okay, so we'll be discussing in detail the rules of the arithmetic. Okay, so let's start with this video. So this is your chapter number 5, more about the 4 rules of the arithmetic. Okay, so now this chapter basically has 5 lessons. So there are a total of 5 lessons in this chapter. The first lesson is integers and rational numbers. The second lesson here is learning how to estimate the calculations. The lesson number 3 here is calculating with decimals and fractions. The lesson number 4 is geometric sequences or geometric sequences or numbers. And the last but not the least, the lesson number 5, which is scientific notation. Okay, so these are your 5 lessons under this chapter. Okay, so let's start with lesson number 1. Let's start with lesson number 1, which is integers and rational numbers. Okay, so before moving to integers and rational numbers, we'll first discuss about what are natural numbers. So natural numbers are basically all the numbers starting from 1. So 1, 2, 3, 4, like that. Okay, so they are the numbers which we usually count and they'll continue to infinity. So starting from 1 till infinity, right? Now on the other hand, when we talk about the whole numbers, so they are all natural numbers, but including 0. So it is basically all the natural numbers including 0. So natural numbers didn't have the 0, so now all numbers have the 0 along with all the natural numbers that we discussed, which is starting from 1 till infinity. So this is going to be 0, 1, 2, 3, 4 and going on till infinity. Now comes the integers. Now when I talk about integers, so they are basically all the whole numbers and their negative counterparts as well. Whole numbers along with their negative counterparts. So what does that mean? So whole numbers were starting from 0 till infinity. Now here we'll be including the negative counterparts as well. So it will be starting from negative infinity, right? Like this. Okay, so this will go on. So this is what your integers are. Okay, now one thing that you have to note here is all the integers belong to the rational numbers and a rational number is a number of the form. So when I talk about rational numbers, so that is a number of the form a over b, where b is not equal to 0. Okay, so this is your rational number. Now we can say that all the integers belong to the rational numbers. Okay, and how do we represent a rational number? So it is basically a over b, where b is not equal to 0. Now what are a and b? A and b both are integers. Okay, so they both are integers. Clear? Now let's take few examples and that will make things more clear. Let's take the first example. The number 4 is an integer as well as a rational number. The number 4 is an integer as well as a rational number. As it can be written without a decimal component, it belongs to integers, right? So when we talk about number 4, so that can be written as directly an integer or 4 over 1, which is a rational number. So this is your rational number representation of 4 and this is your integer representation of 4. Okay, now when we talk about the rational form, so this can also be written as 8 over 2, right? Or its respective negative counterparts, which are negative 8 and negative 2. Yes, so we can rewrite 4 over 1 as 8 over 2 as well as negative 8 over negative 2. Whereas when we talk about 1 over 5, which is by default a rational number, now here this is equal to 0.2, right? Now this is a rational number but not an integer. We cannot rewrite it in the form of integer. So what I'm trying to make you explain is when we talked about 4, so that was an integer as well as rational number, as we have seen that the 4 could be represented as 4 or 4 over 1, but when it comes to 1 over 5, it's a rational number but not an integer. So we can say that rational numbers are the superset of the integers and integers are the subset of the rational numbers. Clear? Now when we talk about a rational number, so there are two different types of rational number. I mean, when I say rational numbers, I mean to say that when they are written in their decimal form. Okay, so there is a fraction form as well as a decimal form. So when I'm talking about the rational number here, so I'm talking about their respective decimal forms. Okay, now when we talk about rational numbers in a decimal form, so it can either be terminating or non-terminating. Or repeating. Okay, so it can either be terminating or repeating. When I say terminating, let's take the example here. Again, let's take the same example, 1 over 5, so it is written as 0.2, right? So now this is a terminating rational number. Okay, but when I take the example of repeating, let's take 5 over 6, so that is written as 0.83333. So this 3 keeps on going, right? So this is what is the case of repeating rational number. Okay, and all rational numbers are the part of real numbers. All rational numbers belong to real numbers. Okay, so all rational number belongs to real numbers. Clear? Okay, so now I'm taking one more example where we are given a decimal form and we are supposed to write in the rational form. So 0.5 can be written as 1 over 2. So this is the decimal form, and this is your rational representation of the same. Okay. Similarly, when we talk about 0.33, now bar here indicates the repeating decimal. Clear? So that means 3 is repeating here. And this can be written as 1 over 3. Now this is the rational form. Clear? Similarly, 0.05 can be written as 1 over 20. Now this is again a rational form. And what kind of decimal it was? So it was a terminating decimal, right? This was also a terminating decimal. Clear? So this was your lesson number 1, where we talked about integers as well as rational numbers. We have seen that all integers are rational numbers, but it's not vice versa, right? We have also seen the example based on that. Then when we represent the rational forms in a decimal when we represent the rational numbers in a decimal form, so it can be either terminating or repeating. We have also seen the examples based on that. We have also defined what are natural numbers, what are whole numbers, right? And how they are different from the integers, right? How do we represent a rational number in the form of a over b, where b is not equal to 0. So this was your pretty much summarization of this lesson number 1 of uh, which is lesson number 1, which is integers and rational numbers. Now let's start with the lesson number 2, which is next. So when I talk about lesson number 2, so that is learning how to estimate the calculations. Learning how to estimate calculations. Learning how to estimate the calculations. Now which calculations I'm talking about? So when I'm talking about the estimation of the calculation here, so what I mean to say is we are trying to quickly estimate the answer of an expression. Okay, so that means quickly estimating the answer of the expression. For example, let's take it as 134 plus 159. Now here this can be approximately, now here when I see the last digit of a number, right, if it is less than 5, okay, so then we round off to the nearest 0. If it is greater than equals to 5, then round off to the nearest 10. Okay, this is how we do the estimation. So now here 4 is less than 5, right? Correct. So we round off this one to 0, so this will be rounded off to 130. Similarly 9, which is greater than 5, so this will be rounded off to 160. So now this the total sum is 290. Clear? So this is the estimation of the given problem. Similarly, you can also estimate the products and quotients as well. This was addition, right? Similarly, you can also estimate the products and quotients as well. When I say products and quotient, I'll give you the example here. Let's say if you are supposed to round off the factors and multiply the factors. Round off the factors and multiply the factors. When I say factors here, so what do I mean by saying that? Let's say if you have 55.8 over 7.42, now this is a quotient, right? Or you can say the division. correct? So now here, if you see the last number, so this is greater than 5, so this will be rounded off to 56. And here the last is less than 5, so this will be rounded off to 0. Okay, and now here in the denominator we also see that we have two decimal places, so you can take them together as well. So like you can take this together, 42, which is less than 5, so this will be rounded off to 0, so that means 7.0. Clear? Now 56 over 7 is 8. I hope that makes sense, right? So this is how we do the estimation in the case of division. Now we can also take the example of multiplication. Multiply the two decimal numbers. So let's say if you have to multiply the two decimal numbers, which are 3.5 and 7.3. Okay, so these are the two decimal numbers that you're supposed to figure out the multiplication for. So what we are going to do is, first we will perform the actual multiplication. So let's do that. Now first I'll be multiplying 5 with the 3, so that will be 15 with the 1 carry, right? Then 3 will be multiplied with 3 with the carry 1, so that is 10. Yes. Now 7 will be multiplied. Okay, then we'll put a cross here. Then 7 is multiplied with 5, so that gives you 35. So here this is 3, and then 7 times 3 plus 3, so that is 21 plus 3, which is 24. Now you can do the sum. So 5, 5, 5, 2. How many decimal places we had? 1 and 2. So this will be after 2 decimal places. Okay, so this becomes your answer. Now this is your answer in decimals. Now you are supposed to round off as well, correct? So now if you round off this one, which is your answer, so you know that this is greater than 5, or you can say 50. So this will be rounded off to 26, right? So this comes when you round off the answer of the multiplication that you perform, correct? Similarly, suppose if you didn't choose to round off the answer, rather you chose to round off the numbers itself, which were the part of the multiplication. So let's do it in a different way. So your numbers were 3.5 multiplied with 7.3, right? So now let's round off them individually and then do the multiplication. So if I round off the first one, so this will be rounded off to 4, and when I round off the second one, so that is 7. So when I multiply them, so I get 28. Yes. So now we see that 28 is not equal to 26, but near about, but similar or near to that, right? So from the approximation, we are not getting exact similar answers, but they are near to each other, correct? Okay, let's take another example. This is the final example of this lesson. So let's say if you have 367 plus 573 plus 135 minus 436. Now you have to, now this is a case of addition as well as subtraction. So this is the case of addition plus subtraction, right? So what you are going to do is you will round off each numbers and then perform the operation. So this will be rounded off to last number is greater than 5, so this will be 370. Last number is less than 5, so this will be 570. Last number is equal to 5, so this will again rounded off to 140, right? And last number is greater than 5, so this will be 440. Okay, so let's do the same addition here. So this is how much? 7, 7, 14, 14, 4. 18. 4, 5, 9, 10 minus 440. So this is equal to 40, 640. So the answer here is 640. Okay, so this is how we do the estimations when it comes to different cases, whether it is addition, multiplication, subtraction, or division. So this was all about the lesson number 2. Now let's move to lesson number 3, which is calculating with decimals and fractions. Calculating with decimals and fractions. Okay, so this is the lesson number 3 of chapter number 5. Now when I say calculating with decimals and fractions, so previously we have seen that how do we calculate the integers. Now it's time to learn how to calculate the decimals. So we have already seen how do we do the calculation for the integers. Now we are going to see how do we calculate with the decimals as well as fractions. So while calculating with decimal numbers, we are going to use the same principles as we used for finding, as we used while calculating for the integers. So we are going to use same principles as we used for calculating the integers. Okay, so let's do that. I'll give you the example. Let's say if you have two decimals in addition, which are 13.6 and 6.4. So what we are going to do is we are going to separate this decimal to a decimal, or you can say a whole number, and to a decimal number separately. So that means this will be written as 13 plus 0.6. This will be written as 6 plus 0.4. Okay, so now what I'm going to do is I'm going to combine the whole numbers and the decimals together. So this is going to be 13 plus 6 and 0.6 plus 0.4. So which is, now this turns out to be 19 and this turns out to be 1. So this is equal to 20. This is how I am doing the calculation with the decimals which were given to me, and those were 13.6 and 6.4. Now suppose rather than having the decimals or the numbers, we have the variables with the decimals. Okay, so let's say if this is the case with the variables, 2.6x plus 3.8x. How do we solve this calculation? So here again we forget that we have a variable here and we perform the usual operation that we have performed in the previous example. So we'll be splitting this to 2 plus 0.6 and we'll be splitting this to 3 plus 0.8. Okay, so basically we are trying to ignore for the time being that we have a variable here. Okay, now once you split, now you can assume that considering that you have a variable here, so this will be written as 2x plus 0.6x and this will be written as 3x plus 0.8x, and then you can combine these decimals which are the whole numbers and the other one which are decimals. So this changes to 2 plus 3 gives you 5 and 0.6 plus 0.8 gives you 1.4x. When you add them, so you get 6.4x. That's your answer. Okay, so this is how we perform the calculation when it comes to the decimals with variables. Now as we know that the decimal numbers are the rational numbers and also can be written in the fraction of two numbers, right? So the way we had seen that the integers were the part of rational numbers, similarly decimals are also the part of rational. So decimal numbers are the rational numbers and can be written as a fraction of two numbers. So this can be written as a fraction of two numbers. So by fraction I mean to say a over b, which is equal to c. Now what is a here? This is your numerator, this is your denominator, and this is your quotient. Correct? Now when we have two fractions that are on the same denominator, so we call them as like fractions. So when the two fractions that are on the same denominator, or you can say that have the same denominator, so they are called as like fractions. They are known as like fractions, and it is easy to add or subtract the like fractions. That's what we also do in the process of finding the greatest common divisor, or you can say the while finding the common denominator, right? We turn our denominator for all the fractions to the same number, and that is how we perform the common denominator process, right? So why do we turn them to the same denominator? Because we are indirectly turning them to the like fraction, so that the addition or the subtraction, or for that matter any operation, becomes easy to perform. Okay, so why do we do that? Because it is easy to add or subtract like fractions. If we add like fractions, we just add the numerators, because the denominators are already same. We add the numerators, okay, and this sum will be the new numerator, while the denominator is still the same. What do I mean by this? Let's take the example. So here let's take the example of 2 over 5 plus 3 over 5. Now here if you see, we have the same denominator, right? Same, correct? So this is what is the example of like fractions. Now when the two fractions are like fractions, so what we simply do is we simply add the numerators. So that means 2 plus 3, and in the denominator it remains same. Okay, so we simply add the numerators, which is 2 plus 3, and the denominator remains same, so this becomes 5 over 5, which is 1. Clear? Now this was your case of addition. Now let's suppose if we are supposed, or if we have to perform the subtraction of the like fraction. Now here again the numerator is equal to denominator, so they are like fractions, right? So what we can do is we can simply perform the subtraction of the numerators, keeping the denominator as same. So this will be 2 over 9. Clear? So this is how we perform the addition and the subtraction of like fractions, and like fractions play important role while making the calculation simple and easy. Now suppose if the denominators are not same, let's say if there are fractions that are not on the same denominator, so they are known as unlike fractions. They are called as unlike fractions. Now the challenge comes that how do we find the sum or the difference of the unlike fractions? how to add or subtract the unlike fractions. Now that's the next thing, right? So in order to add or subtract the unlike fractions, that's when the common denominator process, or you can also say finding the least common divisor, comes into picture. Okay, so to find the common denominator, what do we do? To find the common denominator, we multiply the first fraction by the denominator of the second. So we multiply the first fraction by the denominator of the second. I'll give you the example to make this understand. So let's say if you have 3 over 4 and 2 over 3. Now here you see that 4 is not equal to 3, right? So this is an unlike fraction, right? So now when it is an unlike fractions, we know that now we have to solve it using the common denominator method or the least common divisor. Now how do we find the common denominator of 4 and 3? So common denominator of 4 and 3 is 4 times 3, which is 12. Now once we have the common denominator, what do? We multiply the first fraction with the denominator of the second. Okay, so what is the first fraction here? 3 over 4. What is the denominator of the second? 3. Similarly 2 over 3, and what is the denominator of the other fraction? 4. Okay, so this becomes 3 times 3 over 4 plus 2 times 4 over 3. So this was your fraction, and this is your denominator of the other fraction. Okay, so this is your denominator of. Okay, so once you have this, now you can simplify. So 9 over 4 plus 8 over 3. Sorry, we also figured out the common denominator as 12. So that also we were supposed to write here in the denominator. So this was so we multiply with the first fraction by the denominator of the second fraction. Okay, so now this becomes 9 over 12 plus 8 over 12. Now once we have them as a like fraction, now they are the like fractions, right? They have become the like fractions. Now you know the process. You keep the denominator as it is, and then you just add them. So this will be 17 over 12. That's your answer. Clear? So that's your answer. Now next come is, how do we rewrite a fraction as decimal? Rewrite a fraction as a decimal. How do we rewrite a fraction as a decimal? So that is usually done using the long division method. That we do using the long division method. So what we'll be doing is, let's take the example of 2 divided by 4, which is supposed to be written in the form of decimals. Okay, so we will be dividing 2 by 4. So when I divide 2 by 4, so I know that this is less than 4, right? So 2 is lesser than 4, so we'll place a 0. So that brings the decimal. Then we also place a decimal here. Now then it brings the 0, right? So this now becomes 20. Now we know that 4 times 5 is 20. Yes, subtracting this gives 0, and there was already a 0. This comes here. So the answer here is 0.5. So how do we write 2 over 4? So this is 0.50. Okay, so this is your fraction form, and this is your decimal form. Clear? Let's take another example where you're supposed to write 2 over 3 as decimal. So when we are supposed to write 2 over 3 as decimal, so that is going to be again 2.00 divided by 3. 2 is lesser than 3, so we'll place a 0, then comes the decimal, and then we bring the 0 also, so it will be 20. 3 times 6 is 18, minus 2, then brings another 0. Again it is 6, again 18, subtracting, so this will give you 2, right? Again we will assume a 0 because we already have a decimal in the question, so this will keep going on. Okay, so this will keep going on, so we can write it as 0.6 with a bar because 6 is what is repeating. 6 is what is repeating. Okay, what is the remainder here? This becomes your remainder. Clear? So we have taken the cases of both the fractions. One was a fixed decimal, another one was, or you can say one was dominating decimal, and another one turned out to be a repeating decimal. Okay, now when we multiply fractions, so how do we do that? So when we multiply fractions, so how do we do that? So while doing the multiplication, the numerators are multiplied with each other. So we multiply the numerators, and the denominators will also be multiplied with. Okay, so we multiply the numerators as well as denominators. What do I mean to say by this? So let's say if you have two fractions, x over y, and the another one is a over b. Now this is your first fraction and this is your second fraction, right? So what you are going to do is you will be first multiplying both the numerators, which are x and a, and then you will be multiplying both the denominators, which are y and b. So these are your denominators and these are your numerators. Okay, so this becomes xa over yb. That's your answer. This is how we perform the multiplication of two fractions. Now this was your journal case. Let's take example with the numbers. So let's say if you have 2 over 6 times 5 over 8. So now what you are going to do is you will multiply 2 with the 5 and 6 with the 8 in the denominator. So this is 10 over 48. Now when you simplify this, this is 2 times 5 and this is 2 times 24. This is 5 over 24. Clear? So this is how we perform the multiplication of two fractions. I hope that makes sense. Yeah, so this is how we multiply the two fractions. Now next comes is how do we divide the two fractions? So division of fractions, how do we do that? So when it comes to division of fractions, so you will be multiplying the first fraction by the multiplicative inverse of the second fraction, or you can say the reciprocal of the second fraction. So you multiply the first fraction by multiplicative inverse, or you can say the reciprocal of the second fraction. What do I mean to say by this? Let's say if you have the first fraction as x over y. Okay, so let's say if you have the first fraction as x over y, and the next fraction as, now this is divided by the another fraction which is a over b. So what you are going to do is you will keep the first fraction as it is, okay, but now here you will be taking the multiplicative inverse or reciprocal. So this will be b over a. Okay, so this turns out to be xb over ya. Okay, so a over b has basically turned to b over a. This is what the multiplicative inverse is. I hope that is making sense. So while doing the division, so this is how we perform the division. Example based on numbers: 2 over 6 divided by 5 over 8. So now 2 over 6 remains as it is, and this will be reciprocal, so 8 over 5. So this is 3, 4, so 8 over 15. 8 over 15 is what your answer is. Clear? So this is how we perform the division of the fractions. One last example that I'm going to take in this lesson, and then we'll close this lesson. Suppose if you have to divide 4 by 9. So now 4 is lesser than 9. So what we take is a decimal. This will append a 0 here. Now you know that 9 times 4 is 36. You subtract. This gives you 4. Now you already have a decimal, so you can keep appending the zeros to the remainder. Okay, so again 9 times 4, which is 36. So you know that this will keep on repeating, right? So your answer to this is, your quotient here is 0.4 with a bar. So that means it's a repeating decimal. Okay, so it's a repeating decimal as the answer. Clear? So this was all about lesson number 3, which was calculations with decimals and fractions. Okay. Now the next lesson is geometric sequences of numbers. Geometric sequences of numbers. Lesson number 4 is geometric sequences of numbers. So when I say geometric sequence, what do we understand from this? So it is either the increase or the decrease by a common factor. So it is increase or decrease by a common factor. So that means sequence is either increasing or decreasing by a common factor. We call that as common ratio also. So this is also known as common ratio. Okay, so the other name to common factor is common ratio. What do I mean to say? Let's take the example. Let's take a sequence which is 2, 4, 8, 16, 32. Now here if you see, you're multiplying with 2, and that is how you get the 4, right? Then again multiplying with 2 will give you 8. Multiplying with 2 will give you 16. Multiplying with 2 will give you 32, right? So this 2 becomes your common factor, because this is what the making the series, or sorry, this is what is making the sequence in the increasing order. Okay, suppose if it was -2, then it would have been a decreasing sequence, right? So this is what is known as common factor or common ratio. Clear? So here we have seen that the common ratio is 2. We can also write that in the algebraic expression. So this can also be written in the form of algebraic expression. How do we write it that? So this is written as an, which is your nth term, equals a1, which is your first term, multiplied with r, which is your common ratio, raised to n minus 1. So this is your algebraic expression. Okay, what is an? This is your nth term of the sequence. R is your common ratio. What is a1? The first term. Okay, and what is n? N is your number of terms. Now here, if you go to the sequence above, so what is a1? So from here we can say that a1 is 2. What is r? R is again 2, the common ratio, right? What is an? What is the last term here? 32. What is n? How many terms do we have? 5. Correct. So if you substitute them, these values, in the algebraic expression, so you will see that the left hand side turns out to be equal to right hand side. Let's do that. An is 32. This is your left hand side, and your right hand side here is a1, which is 2. R is again 2, n minus 1, so that is 5 minus 1. 2 times 2 to the 4, 2 times 16, which is 32. Now if you see, they are equal, right? So left hand side is equal to right hand side. So we have validated the algebraic expression that we just wrote above. Okay, now that was your general algebraic expression, but in this case we could have another suggestion to our algebraic expression, and that was, here if you see the terms, so every term is getting multiplied with 2, right? And also we have the first term as 2, so we could have also written the algebraic expression as an equals 2 times 2 to the n minus 1, because this is your first term, and this is a common ratio which is acting as an increasing factor for your sequence. Now suppose if you have to know the next term after 32, which was your last term, right? So how do we do that? So 32 was your fifth term, so that means what is the sixth term, which is your next term, right? What is your sixth term? So how do we do that? We'll be substituting n as 6 in the expression, n as 6 in the expression, and that will give you a of 6 equals 2 times 2 to the 6 minus 1, which is 2 times 2 to the 5, and that is 2 times 32, which is 64. So the next term will be 64. Okay, so sixth term will be 64. Clear? So this is how we find the sixth term. Even if you find it from the previous expression, that will still work. Clear? Final example we'll be taking is, so let's say if you have a sequence as 4, 12, 36 and 108 like this. Okay, so if you have to traverse, so this is multiplied with 3, this is again 3, this is again 3, right? So what is r here? R is 3. What is a, which is your first term in this case? That is 4. So you know that an is equal to, what was an equals to? An equals to a1 times, a1 equals a, so they both are same, they both refer to the first term. So an equals to a times r to the n minus 1. So what is a here? 4. R is 3. What is n? What is n here? Okay, let's take n as 8. Okay, let's assume that n is given as 8, so that will be 8 minus 1, so that is 4 times 3 to the 7, which is 4 times 2, 187, And how much is 4 times 2187? That is 8748. So this becomes your 8th term of the sequence. Clear? So this is how we find the nth term of a sequence. Clear? So this was your lesson number 4, which was geometric sequence of numbers. Now the final lesson, which is scientific notation. So we have the lesson number 5 as scientific notation. Okay, so this is scientific notation. Now when I talk about scientific notations or exponential notation in general, or exponential notation, so when we talk about scientific notation or the exponential notation, why do we call that as exponential? Because this involves e is your standard value as 2.713, right? E is your exponent. So since scientific notations involve exponents, which is e, so that's why we also call that as exponential notation. So it's a handy way to manage extremely large numbers. So why do we use them? So they are basically used to handle or represent the large numbers. So whenever you have large numbers to be represented, so exponential notation or scientific notation makes it easy. Okay, so it's a handy way of managing the extremely large numbers. Okay, for example, Earth's mass, and also now this is extremely large or extremely small also, or extremely small numbers as well. Okay, so when I say extremely small numbers, so that has an example of mass of a hydrogen atom, mass of hydrogen atom. Now this is very small, so that also can be represented using the scientific notation. These type of numbers are not easily manageable, right? So when we talk about these two, so they are not easily manageable, correct? And that is where we make use of scientific notation. Okay, so now when we talk about the scientific notation, we use the base as 10. So we use base 10. So we know that 10 to the 1 is equal to 10, 10 to the 2 is equal to 100, and 10 to the 3 is equal to 1000, right? So as many zeros we have, that becomes the exponent of 10. Clear? So if I have to write 4 times 4000, that is basically 4 times 1000, right? So this can be written as 4 times 10 to the 3. So this is how we reduce a number or a large number to an exponent form. Now when we talk about the mass of Earth, let's say Earth mass is what we are talking about. So that is a lot of zeros, right? How many zeros? 6 with 24 zeros. Okay, so that can be written as 6 times 10 to the 24 units. Okay, so the Earth mass can be represented. So this becomes your scientific notation. Okay, similarly, now this was the way of measuring the extremely large number. Now when it comes to extremely small numbers, so how do we do that? When it comes to extremely small numbers, obviously they will have the decimals, or you can say a lot of decimal numbers, right? So in that case we represent like this. So 0.1 is represented as 1 over 10, which is 1 over 10 to the 1, or you can write it as 10 to the negative 1. 0.01 can be written as 1 over 100, which is 10 to the negative 2. 0.001 can be written as 1000, which is 10 to the negative 3. Okay, so suppose if you have this number, in fact take 3 zeros, so you can write this as 0.001 times 5, and this can be written as 10 to the negative 4. So this will be 5 times 10 to the negative 4. This becomes your scientific notation to this. Okay, and now since I mentioned that this is when we have to figure out the extremely small numbers. Okay, so now here the example would be mass of hydrogen atom, which is extremely small, and that is 0.0017. How many zeros? 28 zeros. Okay, so this can be written as so this is basically 0.00028 zeros and then 1 multiplied with 17. So this is 29 places, right? So it will be 10 to the negative 29 times 17, and then you can simplify this further to 1.7 times 10 to the negative 28 units. Okay, so this is how we convert that to a scientific notation. One final example of this lesson. Let's say if you have to write 4 with 6 zeros, so how do we write that in scientific notation? So this will be 4 times 10 to the 6, right? Because we have 6 zeros. Similarly, 0.000055. How many zeros? 4. So it is 0.0000. Or otherwise you can also calculate it like this. You can calculate it like this. How many decimal places? 6. So it will become 55 times 10 to the negative 6. So it is 55 times 10 to the negative 6. Okay, suppose if you have 4.08, otherwise you can take 408 times 10 to the 4, so that will be 408 and then 4 zeros. This is reverse. Okay, from scientific to the number. Last, negative 0.000732. How do we write that as? So this will be how many decimal? 6 again. So this will be 732 times 10 to the negative 6. Okay, clear? So this is how we convert that to a scientific notation. So this was your chapter number 5. Okay, and that was more about the 4 rules of the arithmetic, wherein we discussed about the 5 different lessons. Okay, so I hope everything that we discuss is clear to you. In case you have any doubts, you can always post me those doubts in the comment section. Okay, and I'll be happy to help. Okay, so that's all for today. If you found this helpful, please don't forget to like, share and subscribe to my channel. Your support motivates me in keep creating this content with love and dedication. I would love to hear your thoughts, and please let me know in the comments how you like this video and any suggestions you have for the improvement. Thank you so much. Bye.